Good morning, everyone. My name is Heidi Hodkinson, and I'm going to talk about my MSc project that I've just completed with the Open University. And I was looking into the analysis of exoplanet transit timing variations, or TTVs for short. So, inspired by Exoclock and the available open source software for analysing TTVs, I wondered if there an opportunity to widen the TTV analysis community to amateurs and students within a pro-am collaboration and by using a GUI-led TTV analysis package. Well, I hope to show you how I came to this question. Okay. Over 5,000 exoplanets have been discovered to date, as we've already seen, and most of those have actually been discovered by the transit method, and largely thanks to NASA's Kepler and then later K2 mission, which is responsible for those jumps in the numbers of confirmed exoplanets that you can see in 2014 and 2016. So add to that the launch of the Transiting Exoplanet Survey test in 2018, and as we've seen already, it's already provided us with over 300 confirmed exoplanets so far. So you add to this the numerous other existing and planned ground and space-based observation campaigns, and these numbers are only going to continue to rapidly rise. And likewise, the number of exoplanets exhibiting TTVs, which back in 2014 were estimated to occur in around 3 to 10% of Kepler planetary systems. So as we've just seen, in the absence of a gravitational perturber, an exoplanet orbiting its host star may be seen to be transiting at a regular set time like clockwork. However, if this exoplanet is joined by a companion, shown here as a larger exoplanet orbiting inside that of the smaller exoplanet, and they orbit close enough together that the inner exoplanet gravitationally perturbs the outer, then this perturbed outer exoplanet will transit its host star at slightly different times than expected of a non-perturbed exoplanet, sometimes arriving earlier, sometimes arriving later. There are other causes of TTVs, again, as we've just seen, such as orbital decay, when an exoplanet is gradually spiraling in towards its host star as a result of the strong gravitational tides caused by the exoplanet and host star interaction. However, the focus here is on those caused by the gravitational perturbation of another exoplanet, whether also transiting or not. Now, over time, these TTVs can be plotted on an O-C diagram, where O is the observed time that the exoplanet transits its host star on its perturbed non-Keplerian orbit, minus C, the calculated time, i.e. the time of transit expected if the exoplanet was following a purely unperturbed Keplerian orbit. So you can see here an example of an O-C diagram, in this case for the exoplanet TRES-3b, which I was fortunate enough to capture 3 transit observations of using the Open University's Pirate Robotic Telescope on Mount Teed in Tenerife. You can see here that the TTVs range to around plus or minus 7 minutes or so. Now, TRES-3b currently appears to be the lone exoplanet in its system, but something as yet unknown is causing those TTVs. While it may yet prove to be orbital decay, it is actually very unlikely to be an undetected, non-transiting exoplanet companion. Okay, so we'll just have a look at mean motion resonance first. So considering pairs of exoplanets in a system, when the ratio of the orbital periods is an integer, they are said to be in mean motion resonance, or MMR for short, which is an unstable configuration for planets that get close enough to gravitationally perturb one another. Now, there are many examples of this on our own solar system, such as in the asteroid belt, where gaps with no orbiting asteroids, known as the Kirkwood gaps, are locations where any object orbiting in them would actually be in MMR with Jupiter, but being unstable, these gaps have cleared over time. Now, first order MMR simply means that the difference between those orbital periods is 1, so j to the j minus 1. For example, that 2-to-1 MMR Kirkwood gap shown here. Second order MMR is a difference of 2, so j to the j minus 2. For example, those 3-to-1 and 5-to-2 MMR Kirkwood gaps, and so on for higher orders. Gravitational perturbation, and hence TTVs, are largest for exoplanet pairs in MMR, and thus we are more likely to be able to detect them. But as this configuration is unstable, most are not actually in this state. And as the distance to resonance increases, the gravitational perturbation and thus those TTVs decrease in strength. However, a significant fraction of exoplanets are near MMR, and Lithic, Xi and Wu, in their 2012 paper, observed that the TTV signals, excuse me, those O-C data points plotted over time for such exoplanet pairs will trace out an almost sinusoidal curve. Thus, they also identified a TTV period, known as the super period, relating that to the orbital periods of each exoplanet in such a pair, and J, that integer difference between those periods. You can see here that these Kepler data points span from about half a super period of Kepler 50b, although that's assuming the continuation of what looks like a sinusoidal trend, to around the approximately 4 super periods of Kepler 25b. Lithic, Xi and Wu then derived their foundational set of analytic equations, starting with Newton's equations of motion, describing a pair of exoplanets with low eccentricity orbits near first-order MMR, and relating these to those TTV signals, which they approximated as sinusoidal, to give wave equations for each exoplanet in the pair. Now, the size of the TTV, i.e. that the amplitude of the wave, is a function of the period of the exoplanet and the distance to resonance, MMR, and the eccentricity of the two exoplanets, and the ratio of the mass of the other exoplanet to the host star. So if we already have the mass of the host star, we can therefore work out the mass of that other exoplanet in the pair from the TTV signal. However, now we're faced with a mass eccentricity degeneracy, or to put it simply, you struggle to tell the difference between the mass and the eccentricity. You can't break them apart because the same TTV signal can be produced by a planet of low mass and high eccentricity and one of high mass and low eccentricity. Now, although Lithic, Xi and Wu's equations can give upper mass limits, they acknowledge that this degeneracy needs other data to be broken, such as detailed knowledge of the TTV phases or other components of this TTV signal. So along with that dominant near sinusoidal TTV signal, much lower amplitude, higher frequency chopping signals may also be observable when the two exoplanets in a pair pass each other on their respective orbits around their closest approach, known as planetary conjunction. That's just shown on the left there. Analytic equations have been derived for this chopping signal, and they can help to break that mass eccentricity degeneracy because they are only dependent upon the exoplanet mass and not on the eccentricity. So here you can see the observed whole TTV signal on the right. That is a combination of the sinusoidal and, well, near sinusoidal and chopping components, and then the chopping signal on its own. TTV signals also contain components relating to higher order MMRs, and analytic equations have been derived for near second order MMR, where the balance between first and second order MMR effects in that detected TTV signal depends on the distance to each of those resonances. Formulae have also been derived to combine all three of these TTV signal components, near first and second order MMR, and the chopping. For the rarer cases of exoplanets in MMR, a different set of analytic formulae apply altogether, as this is a more dynamically complex configuration. So, okay, assuming we have a set of TTV observations for one or more exoplanets in a system, and host star data, and an exoplanet system that we think will fit within the limitations of these analytic formulae, the trick is to somehow input all of that information into these equations, and then hope that the output is a set of orbital parameters exactly describing the whole exoplanetary system responsible for those observed TTVs. But of course, it's way more complicated than that. For all but the simplest of planet pair systems, manual application of these complex analytic formulae becomes far too unwieldy. Fortunately, the process has been partially automated in the form of the semi-analytic methods, essentially those analytic formulae turned into computer code. Although we have to remember that these are limited to specific exoplanetary system architectures because they have been devised for limited configurations of exoplanets moving around their host stars. And, for example, we already know that the analytic equations of Lithic, Xi and Wu are approximate solutions for exoplanet pairs near first-order MMR, because they describe those TTV signals exactly as sinusoidal, which they are very close to, but not exact. Alternatively, without the limitations of the analytic formulae, exoplanetary systems can be simulated by integrating Newton's equations of motion, which essentially means calculating the relative positions and velocities of every exoplanet and host star in a system at regular steps along the orbits of each of those bodies. However, this is very computationally expensive, and we also now encounter the n-body problem, whereby we're only ever going to be able to approximate Newton's equations of motion for more than 2 bodies in a system. Fortunately, much R&D has gone into developing suitable n-body integrators that don't accumulate or are able to correct for errors over time, whether simulating over several years of TTV observations or fractions of exoplanetary system lifetimes. Thus, we also have these numeric methods, essentially n-body integrators customized for TTV analysis. So now we can input all of our observational data along with likely ranges for the unknown parameters, and these semi-analytic and numeric methods will output model TTVs that can be matched to the observed TTVs. However, many different combinations of orbital parameters can produce the same TTV signals. So first we need to narrow down all of these matching model TTVs, and we can do this using Bayes' theorem, specifically Bayesian inference methods, which calculate outcomes based on probability and likelihood informed by prior data and theory, and which are used across all scientific disciplines. And as with the integrators, there are certain tried and tested methods, algorithms, that can be deployed and will select the model TTVs whose orbital parameters best fit those observed TTVs. The results of numeric methods can also be checked using the analytic equations of, say, Lithic, Xi, and Wu, as long as the exoplanetary architecture fits within the limits of those equations. And finally, the solutions can be run through another n-body integrator that will simulate the whole exoplanetary system over a fraction of its lifetime to check that the proposed solutions are stable. Although, as I'm sure you can imagine, it takes a long time to carry out these simulations. So prior to running these computationally expensive integrations, you can carry out a rough stability check by applying the Hill criteria. Essentially, the Hill radius or sphere of a body represents the distance or volume within which any passing object will be dominated by the gravitational field of that body and not the central star. So passing the Hill criteria indicates that the planetary configuration will likely remain stable. However, this only works well for those in very low eccentricity orbits, and it also doesn't work so well for planets near MMR. So you shouldn't use this in place of a full n-body stability assessment, but it is useful as an initial check. And now we can find out what orbital parameters of what combination of exoplanets computationally generated those model TTVs that best match the observational data and remain stable. For example, TTV data from the transiting Kepler-46b indicated the presence of a gravitationally perturbing companion. N-body integration was then used to simulate a 2-planet scenario and generating model TTVs that were narrowed down using a nested sampling algorithm. And the result was tested via another N-body integration that was run over approximately 100 megayears. From this, it was estimated that Kepler-46b is roughly the mass of Jupiter and Kepler-46c about half that. Over the past decade or so, many papers have devised their own method to analyze TTVs, but repeating this work for each TTV analysis isn't particularly efficient. Therefore, I went on the search for open source TTV specific methods and found 3 main methods that stood out from the crowd for their consistent use. The numeric method Trades, Transits and Dynamics of Exoplanetary Systems was published in 2014 by Borsato et al. Although written in Fortran 90, it is also available for use with Python. TRADES uses a fast and highly accurate integrator and can also simultaneously analyze radial velocity data, RV data, which can help to better constrain those resulting orbital parameters, and the examples of its use in the literature all take advantage of this. In the same year, TTV Fast was released by Deck et al. This was developed from a type of integrator usually reserved for those long-term stability assessments, as it preserves energy much better over these timescales compared to regular integrators. Although this type of integrator is not usually necessary for TTV observational timescales, they are much faster than regular integrators. However, this is at the expense of some accuracy, although the developers of TTV Fast note that the accuracy is still within observational error. TTV Fast can also analyze RV data, excuse me, although in the literature where TTV Fast is used for TTV analysis and RV data is available, it is actually generally analyzed using a separate RV-specific analysis method, such as RADVEL, developed by Fulton et al. In 2018. From two of the same developers of TTV Fast came the Semianalytic TTV Faster in 2016, available in C, IDL, Julia, and Python. It was tested to be around 400 times faster than TTV Fast and with similar accuracy. So while TTV Faster clearly wins the speed race, being an analytic, as it was generated from analytic formulae, it does also suffer from some limitations and doesn't take RV data. Now, TTV Fast is actually by far the most popular, with TRADES and TTV Faster coming in joint second but way behind, which may be due to computational resource still being a prime consideration and those analytic limitations. However, a potential downside to each of these and other similar TTV-specific methods is that you need to be able to code, including combining them with other methods to narrow your results and assess stability. You still end up with a very complex process, even with the availability of TTV-specific methods, especially when you start to include processing of raw data prior to TTV analysis. An application programming interface, an API, to bring all these processes together could therefore be really, really helpful. And over the last 4 years, there have been attempts to create such, but one of these really stood out to me. The Exostriker. This was developed and released by Trifonov in 2019 and able to combine TTV and RV data, and there are plans for further development. But what makes the Exostriker particularly appealing and unique is its GUI, meaning that it is, to my knowledge, the only open source TTV analysis API that does not require coding skills to run. The Exostriker currently links to TTV Fast, and the developers are planning an inbuilt TTV analysis method as well, but state that you will still also be able to use TTV Fast. So, with this GUI-led API, is it feasible for TTV analysis to be carried out by pro-am collaboration? Could, for example, the ExoClock software hops be extended with a simplified version of the Exostriker so that it will work on a home PC as hops does? As it stands, the Exostriker runs on Linux, not Linux, but you can fairly easily download a Windows-based version of that now. The main issue, I think, is the computational resource required to run it. I struggled on my 8 gig RAM PC, but I don't think it required much more than that to run properly. It would also be good if the RV analysis function could be retained, but perhaps the long-term stability assessments could be foregone and just a Hill criteria check left in place. Perhaps the API could link to the less resource-heavy TTV Faster in place of TTV Fast, albeit with some exoplanetary system architecture limitations to consider. Another option may be to make computing resources available if possible. Clearly, this all requires much research and would make a really good future project. Oh, yeah. So yeah, thank you for listening, everybody. Does anybody have any questions?
Thank you, Heidi.
Thank you.
Thank you, Heidi. It seems to be something that could be very useful to us mere amateurs. And I was worried I wouldn't understand what you were going to say, but I think I got the gist of it anyway. I'm sure when I get your PDF and look at the video again, I'll fully understand it. But, are you carrying on with this work?
No, I mean, I've just finished my MSc and I'm now going out to go and get a job. So I'm not going to be carrying on with it, unfortunately.
That's a shame.
Yeah, that is a shame. It's one of the kind of, you get the time when you do the really interesting stuff, and then sometimes the real world hits.
Unfortunately, yes. I mean, if I was independently wealthy, then yes, I would happily carry on doing this.
And we have a couple of comments, a brilliant from Emily and a thank you from Jessica. And Seafreak has a question. Have you considered combining TTV fast with nested sampling methods like UltraNest? We are working with this now? Question mark.
Yeah, I've come across, whenever I've seen TTV fast used, everybody's either used it. Well, most people have actually used it with MC, the MC Markov chain Monte Carlo. Is that MCMC algorithm for narrowing those results? And some people have used it with a nested sampler, usually multi-nest. And then I've also seen on GitHub that some people have very helpfully combined TTV fast. I've seen it combined with MC, open source for people to use. I don't think I've seen open source yet combined with multi-nest. But yeah, I think there's definitely scope to provide that for people. I think from a pro-am perspective, I think it's the GUI that's really going to help as well. But yeah, certainly having a combination of those two would be very helpful.
Excellent, thank you.
Right, thank you, Heidi.